Hello everyone, welcome back if you attended the first tutorial session, and welcome if you're just joining us now. So just to recap, in the first session we introduced gem5-X and provided a hands-on tutorial on how to run and use gem5-X. We also premiered GXR5, our RISC-V extension for gem5, as well as covered some useful features and techniques. In this session we will focus on optimizing and extending architectures with gem5-X and GXR5. In particular, I will demonstrate extending the ARMv8 ISA in gem5-X, as well as discuss how you can also do the same in GXR5 with the RISC-V ISA. In addition to that, I'll also discuss adding devices to your SoC after you've extended the ISA. So first of all, why would you want to extend the ISA to begin with? In general, ISAs have unused opcodes that are left open for new extensions. This gives us room to enhance the capabilities of our CPU with new and specialized instructions, such as through the use of a new functional unit or accelerator. It is also important to compartmentalize extensions in RISC ISAs like ARM and RISC-V because small embedded systems trying to meet cost and power constraints may not need advanced capabilities such as vector extensions or even floating point. On the flip side, high-performance systems using these RISC ISAs may require the aforementioned extensions for high-level applications and benchmarks. All that said, if you're familiar with HDL or other low-level modeling methods, the idea of extending an ISA for your research may be a little bit daunting. For example, for every CPU model you want to explore, you will need to modify its decoder as well as numerous other components, potentially on a per-model basis, depending on your extended ISA's capabilities. Of course, there are methods you can use to reduce the overhead of modeling your ISA extension in HDL, but in Gem5, it is actually incredibly straightforward. So what you need is simply your new instruction definition, an idea of your new instruction characteristics, and at the end of the day, you only need to modify 7 files in total to extend your ISA plus 1 or 2 additional files per CPU model you want to extend the ISA for. Basically, the way extending ISAs in Gem5 works is to first add statistics tracking for your custom instruction to the base CPU model. Second, add the new functional unit to your CPU model. Third, define the instruction and functionality in your ISA microarchitecture. And 4, recompile Gem5. And that's it. So for a hands-on example, let us now add a new instruction in Gem5. In this example, I'm going to walk you through the add1 test that is included with Gem5-X and described in the Gem5-X technical manual. This toy example sets up the basis for which you can simulate new accelerators integrated as functional units within your CPU. The instruction we are adding here is add1 in the ARMv8 ISA. It is the same as the add instruction in the same ISA, but it uses an unused opcode. Note that the steps I outline here are going to be the same for Gem5-X as they are for GXR5. The primary difference is that in GXR5, instead of using ARM ISA files located in source arch ARM ISA, you would use the RISC-V ISA decoder in source arch RISC-V ISA. In addition to that, of course, the actual instruction format differs slightly, but it is actually much simpler to modify the ISA in RISC-V, so this example will prepare you for both. As one final note as well, it is exactly this toy example that established the basis for the binary dot product engine paper published in VLSI SOC 2019, as well as current research projects that I am working on. So not only can you use this example for architectural exploration, you can publish with it as well. The files you will need to modify are listed here. Essentially, what you are adding here is a new instruction type that can be tracked in the Gem5 statistics file at the output of your Gem5 run. In the inst.proto file, you are simply adding an index for your custom instruction enumeration. In the execcontext.cc file, you are adding the stats variable that tracks how many times the instruction was called. And finally, in the base.cc file, you are adding the statistics name and feature to the stats file for gem5, as well as incrementing the stat every time the instruction is run. The next step for adding this new instruction to gem5 is to add the functional units to our CPU models. For the base CPU model, we add the op class name in both functunit.py and opclass.hh. This will be the generated C++ class for our new custom instruction. Now we need to add this functional unit to our CPU models. First, in the minor CPU model, aka the in-order core model, you want to make a child class that uses our aforementioned op class definition, as well as add this new functional unit class to the functional unit pool. Note that this oplat variable is where you would set the number of cycles it takes to perform this operation. So if you were implementing a custom instruction that does a lot more than add, and you found in your preliminary test that it should have an op latency of, say, 12 instead of 6, you would just modify this number here. After you've done this, we can now modify the out-of-order core model. Similar to before, you want to add a child class that uses the aforementioned op class definition, as well as add this new functional unit class to the functional unit pool. The O3 model separates these into two files, so you just add the custom ALU to default fupool and fupool.py, and then the custom ALU class definition to functional unit config.py. Just like before, you can set your op latency in the fu class definition here, but instead of having a separate variable for it, you use an argument in the opdesc instantiation. The count variable here is the actual number of functional units dedicated to the custom ALU in your O3 core model. The next step is to now actually extend the ISA. For ARM, this requires that we modify two files in the gem5-X source arch ARM ISA folder. Note that for RISC-V and GXR5, you would only need to modify the decoder file in the source arch RISC-V ISA folder. Note that these .isa files that are listed here are actually in Gem5's domain-specific language, or DSL. However, the Gem5 creators were smart enough to not make something so complicated as to require learning a whole new language. You can basically treat definitions as Python-like code and implementations as C++-like code. So in AR64.isa, we are defining how our instruction is actually decoded, as well as the existence of a pointer to the instruction class. In our case, our custom instruction has bits 27 to 30 set to 0, and then bits 23 to 25 set to 2. So it is here that we return our new custom instruction object. Note that as you can see in the code around here, there are a lot of return unknown 64 statements. This basically leaves you room to implement multiple custom instructions if need be, in case you wanted to implement 2, 3, or even more instructions instead of just the single add one. Then in data64.isa, we actually define the functionality of our new instruction. ARM actually gives us helper functions to define new instructions with. This build data instruction uses one destination register, dest64, one argument register, op164, and then an immediate secop. Note that if you wanted to use, say, a multiple register argument instruction format, there's another helper function called build.dataxreginst for that. This same file, data64.isa, actually has numerous examples of the various helper functions you could use to extend your ISA in many different ways. But anyway, as you can see, this is where we add our instruction functionality, as well as the instruction mnemonic and the op class that we had from before. If you wanted to change add one to, say, add an immediate value in a register and 1, I would simply do dest64 equals restemp equals op164 plus secop plus 1 semicolon. As I said before, this is basic C++ code, so you could really do whatever you like here. So anyway, that's it. At this point, our custom instruction is implemented, and all we have to do is recompile gem5, and you're ready to use the new custom instruction. So you may be asking yourself at this point, I have this in custom instruction now, but how do I test and use it? How do I know that I actually did everything correctly? Thankfully, this process is relatively easy as well. To test our new custom instruction, all you will need to do is use some inline assembly. In C/C++, this is easy because you can just use the built-in ASM method. Here I have pictured from the add1 test example the exact ASM you would use for this instruction. We take out input to this function in1 and move it into register x9. The custom instruction is then run using both x9 as the Rn input and the Rd output. The result is then retrieved from register x9 and placed into this result res variable and returned for whatever high-level function we want to use it for. So now that we've done everything here, I will quickly go over to my virtual machine and demo this in action. Alright, let's get started with the demo. So in the VM, if I go to the downloads folder in LS, you can see that I have a modified files folder and associated zip file, as well as an add1 test folder and associated zip file. In the modified files folder, you will see that we have all of the files I previously mentioned in the lecture, all modified to add the custom instruction, as well as this modified file list file. In the file list file, you can see the actual locations for all of the files. So a simple way to implement the custom instruction from the tutorial is to simply copy all of these files to the associated locations in gem5-X. Just a note, if you do get an argument definition error or a function definition error, when you rebuild gem5, that is referring to source simple base.cc. Basically, there's an inconsistent function definition on line 476 of base.cc in source CPU simple. If you just copy the argument from the associated function in base.hh in that same folder, that should resolve the error, and you can rebuild gem5 again. So that's everything in modified file list, and in this case I did indeed just copy all the files over, rebuild gem5, so that is all ready to go. In addition to this, I have the add1 test folder, which contains the code, a compilation script, as well as the binary for this code. Now, if I cat add1 test.cpp, and I scroll up, you can see the same addition function I showed off in lecture, where we take this input in 1, move it to register x9, run our custom instruction with x9 as both our input and output register, and then move the output that's in x9 to whatever our result res is. So we took this function and we put it into this main, where you can see we declare one array of 10 integers, 10, 20, 30, 40, etc. And then we have a for loop where we copy the values of this array into a new array, but we also apply this addition function. Now the custom instruction up here has the immediate hard-coded to 3. So if this C program works as intended, basically C should contain the values 13, 23, 33, 43, etc. Now, to demo this, what I'm actually going to do is use 9p over Virtio to access the add1 binary in the shared folder. So if I go to scripts, you can see that I have this run gem5-X add1.sh that actually restores a checkpoint from the 9p over Virtio demo. And if I do ls shared, you can see the add1 binary is indeed right there. So to get started with this, I will do the run gem5-X add1.sh, which you can see in the command line is the same as the 9p over Virtio demo script, except I add this restore the first checkpoint variable. Now keep in mind I already copied over the custom instruction files, I already recompiled gem5, so this is running with the custom instruction right now. And then to actually run the demo program, I will do telnet localhost 3456, and you can see we're already at the command line. So now I'm going to do sh mount.sh home/conferences/scripts/shared, basically the location on the host where our add1 binary is going to be. And just to make sure it works, when it's done running, I'm going to ls/mount. You can see that gem5 does indeed have access to this folder, and add1 does exist. Now, if I do ls/al, sorry, not in the current directory, if I do ls/al in/mount, you can see that add1 does indeed have read, write, and execute permissions on it. Note that if you just copied it over directly and you didn't change anything, you might see that it only has read and write permissions on it, in which case, just from within gem5, you do chmod 777/mount/add1. And that would ensure that you could indeed run the add1 binary. So that said, let me actually run it now. And you see, yep, as expected, our array C has the values 13, 23, 33, etc., all running the custom instruction. Now I can do an M5 exit to exit the simulation. And then next what I can do is actually go to the output folder for this later run, so latest run, I mean. So if I do cd gem5-X 9p output, you see that we have all of our checkpoints, our config, our stats, etc. And now I want to open the stats file, and I'm going to do a search for cusalu. And you can see that from our output statistics, the system CPU op class cusalu ran 10 custom instructions as expected. And right, so that concludes the demo for the custom instruction extension. So now that we know how to extend the ISA in gem5/GXR5, we naturally want to better understand our limitations of our simulation. The primary obstacle that arises from implementing an accelerator in this way is the need to use non-volatile data structures. Even in the binary dot product engine paper, kernels were selected from memory, then used to perform the convolution. Now there's multiple ways to go about implementing non-volatile data access to our instruction. One method could be to use a memory load type of instruction to actually load stored data from memory or storage. This would require using a different instruction format, and the implementation in gem5 would be slightly different than what I outlined previously. Another method could be to simply hard code non-volatile data into the instruction definition itself. Recall that in the data64.isa file, we simply use C++ to implement the functionality of our add1 instruction, i.e. we use a constant array to access hard-coded values. The method I will describe today, though, to handle non-volatile data structures through custom instruction access uses SOC devices. SOC devices in gem5 are objects separated from the ISA. By establishing a common interface, you could add a custom device to your SOC and then access it via your custom instruction. One note I should mention here, however, is that all of these suggested implementation methods are viable for different kinds of architectures and applications depending on what you want to explore. There is no best answer here, though in my opinion, however, adding a SOC device is the best method when you want true ISA and device separation for applications where you may have more than one way to access your accelerator. So in this follow-up demonstration, I am going to use our add1 custom instruction enabled system, but offload the add1 functionality to a custom SOC device. Just like before, the concepts and implementation here in gem5-X are applicable to GXR5, but it is inevitably simpler in GXR5 due to a simpler SOC configuration. So as you can see here, we will keep the same instruction definition, as well as the same instruction assembly and format. But to show the capabilities of this new SOC-enabled instruction, I'm going to modify the instruction's function to return the sum of Rn and your immediate value and this plus plus x variable. In this case, x is going to be a variable held in the SOC device that increments by 1 every time the instruction is called, and is subsequently added to RD. The way I will implement this device is as a custom peripheral I/O or PIO device sitting on top of our ARM RealView platform. So to show roughly what the system configuration will look like, I have a diagram here showing the CPU model, SoC, and the bus that connects the two. Over here is the CPU model, where at some point within its pipeline there is an execute stage that can run the custom instruction. And on this side is our SoC, which houses the peripherals, including our custom device for the add1 instruction. Now, while we could use the I/O bus to interface the device, what we'll be modeling here with our add1 custom device is a direct line between the CPU and device, which I have highlighted here. Since we won't be using the shared I/O bus, we can model very fast response times between the device and the CPU. Now, implementing this device does take a bit more code than the ISA extension example, but it is still relatively straightforward. I'll cover the high-level implementation details, and then the rest of the code is provided for you. So, the steps required to implement an add1 SoC device are as follows. First, we have to create the C++ device model and implement its methods. Next, we have to use Python to add this device to our SoC configuration. Then we will use the gem5 system object to add a connection between our custom instruction and the SoC device. And finally, we just recompile gem5 as before, and that's it. So for the first step, we need to add the new device. We implement the new device in C++ using a header and associated implementation file, in this case, customdevice.cc and HH. In general, all device models in Gem5, ISA specific or not, are located in source/dev. Here I have pictured the header definition for the custom device class. As you can see, it inherits from the basic PIO device class, which has some required methods which are at the bottom there. The most important parts of the class are the private variables and the add method. The ARM system object is a pointer that will allow the custom instruction to interface the device directly and vice versa. And then the integer x is that non-volatile variable we are demonstrating. And finally, the add method is what we will call in the custom instruction to produce the result. To ensure that the device is built into our system, we also need to add the implementation file to the list of sources in the scan script. This will tell the build system to compile the custom device along with everything else. You will also see here that I added a debug flag for the custom device. If you are aware of Gem5's debugging utilities, this is where you add that flag. If not, I would be happy to discuss and go over it during the Q&A. Next, we need to add our device to the system config. Since we are using ARM and gem5-X, this means adding our device to the RealView platform. Note that in GXR5, you would be using RISC-V and the simple board platform for this, but the process is pretty similar. It is in this Python file that we both define the existence of the custom device class, as shown here, as well as add it to the RealView platform itself. And then there are a couple other methods not shown here where you would add it to a list of peripheral I/O devices, which are then used by ARM's predefined helper functions. And finally, before we compile Gem5, we need to interface our custom instruction through the system object. First, we add both a self-referential system object and custom device pointer to our system object. The custom device uses the self-referential object later during the instantiation of the whole system. Then in our ISA includes file, we add both the system and the custom device headers, which will ensure that these header files are compiled as the new instructions are generated. And finally, we adjust our custom instruction definition to use our custom device. As you can see in the code here, through the system, we get a pointer to the custom device, and then to get the result, we use the pointer to the custom device and call its add function using op164 and secop, aka the immediate, as the arguments, and then store the result in desc64. So then to test our custom device integrated with our ISA extension, we will use the same test program as before, where we send an input to register X9, call the custom instruction, and then retrieve the result from register X9 again. So allow me to jump to the virtual machine now for the demo. Alright, now for this last demo, let me go over to my downloads folder, or files again. You see I have this modified files SOC folder and associated zip. So just like the previous demo with modified files SOC folder has all of the files you need to modify in it, in addition to those that you already copied over from the modified files for the add1 test and the extended ISA. So again, an easy way to implement the custom SOC device without jumping through all the hoops of figuring out every little bit of the code is to simply copy all of these files to the specified file locations, and of course the specified file locations are in the modified files list, as you can see here. So that said, just like before, I copied over all these files, I recompiled gem5, and then I ran it using one of the scripts in the scripts folder. So you can see here, I ran it from the start, didn't have any errors except for the usual warnings. And if I go over to the telnet window, you can see I'm at root at localhost again. So if I do sh mount.sh again, /home /conference sliz /grip /shared. Oh yes, this is the 9p over Virtio version of gem5-X running right now. So if I do ls/mount, you can see the add1 binary is there just as before, and if I do ls-al/mount, we still have permission to execute it, which is good. So remember before that the add1 code basically had us copying values from one array to another and adding a hard-coded immediate of 3 to each of those values. So 10 became 13, 20 became 23, 30 became 33, and so on. So in this case, we're also adding this variable x, which is being held in our SOC device. And we're incrementing x every time we call the instruction. So in this case, for the first time we call the instruction, 10 will turn to 13, but then 13 plus 1, so it becomes 14. The next time we call the instruction, 20 is going to become 20 plus 3 plus 2, because we incremented x again, and so on. And so if I run /mount/add1, we should see this pattern realized. And indeed, that's what we see. The first value is 14, then 25, then 36, then 47, then 58, etc. Now at this point, because we've run the custom instruction 10 times, x should now be 10, which means if I run this again, c at 0 should actually be 24, because remember, we're still copying over an initial value of 10 and adding the hard-coded 3 from the custom instruction, but now x is going to initially be 10 instead of 0. So if I run this again, you can see, indeed, C0 is now 24, C1 is now 35, C2 is now 46, and so on. And if I run this yet again, now it's 34, 45, 56, and so on. So this is how we know that the non-volatile storage capabilities of the SOC device are working as intended. And so at this point, I think we're ready to open it up to an extended Q&A, and thank you everybody for coming to High Peak, and thank you all for your time.